Hello everyone, welcome to the Cambridge University Astronomical Society's weekly talk. Tonight we have Joshua Lovell with us to share more about planetary systems and how they are formed. So before we begin, let me just give a bit of introduction about who our speaker is. Joshua is a final year PhD student in the Institute of Astronomy at the University of Cambridge. His research is focused on understanding the formation and evolution of planetary systems following the dispersal of the protoplanetary disk and through the main sequence, when it is expected that only planets and planetesimals remain. He observes, analyzes, and models the circumstantial dust and gas of populations of disks, and conducts detailed investigations of the individual systems, primarily with high-resolution sub-mm ALMA image. To probe the different regions of and processes within planetary systems, he works with scattered light images, near and infrared IR spectroscopic data, and multi-wavelength photometry. He is also involved in a number of ongoing projects analyzing stellar and disk demographics in young star-forming regions and modeling the morphology of debris disks. Without further ado, Joshua, please.
Thank you very much. So thank you very much. I'm going through job applications round at the moment. So that's probably something that I've sent to an employer potentially before anyway recently. Yeah. I'm Josh. As has been said, I'm a PhD student over at the Institute of Astronomy, which is down Madden Road here in Cambridge. And I try and understand how planetary systems form, when they form, why they look like they do, when they evolve over many millions and billions of years. I wanted to start today by showing this image here. Partly because I got it as an anniversary gift in a 50 by 50 block a few months ago, and I saw it, I was like, wow, this is incredible. But really because what it shows you is what's going on inside our solar system. And this basically has plotted every bit of light on this image here, has any body in the solar system that we know about that's at least 10 kilometers in size. Admittedly, it doesn't have the Oort cloud. But what it shows you is, okay, so we've got the star in the center of our sun, we've got a few planets. Then we've got this giant region here where there is just tons of material, tons of asteroids, thousands of them there. You've then got these two great big red bands here and here. And these are asteroids that Jupiter's captured. Then you've got some planets out here, so you've got Jupiter and Saturn, you've got, broadly speaking, a big gap. Eventually you find Uranus and Neptune, and then you have another big band of asteroids and comets out here. And I guess the point I really want to make today in this talk is when we talk about planetary systems, we're talking about the planets and all of these other bodies as well. They will have unique importance in terms of understanding the formation of the entire solar system and the stars. So, oh no. Right, I'm just going to move to clicks. There we go. Okay, I've got control now. So what I wanted to broadly say is my talk. What I'm trying to do in my talk. What I'm trying to do is say, how do we go from giant structures like this that we see in our galaxy? This is the Orion Nebula. In fact, this is Orion's belt here. How do we go from these giant structures of gas and dust that we see in our universe and in our galaxy, and end up with systems that look like this? So what we've got again is the solar system, another version of it, a representation of it. We get these beautiful things. We get Earth that looks like this. We get asteroids that look like 67P that have dust being blown out of them. We have comets that shoot through our solar system.
Good as well, supposed to do.
into these big belt structures that we can observe, and I'll show you some in a short while. The same is true out here as well. Okay, and also we have these comets as well that might take thousands of years to travel all the way into the inner solar system. As they do so, release gas, release dust that trace their orbits as well. So all of this stuff, all of that is what I'm talking about when I'm referring to a planetary system. So the planets, the planet rings, the moons, and then the planetary system disks and debris. Okay, and I focus a bit more on this stuff later in the talk. Because what I want to say a little bit first is about how we're going to observe these things. So some of this might be elementary for people here, but I wanted to start the talk at least from a place where everybody's going to understand what I'm going to talk about later. So observing planets. How do we observe planets? Planets are observed in many ways. Okay, so in fact, the most common way that we observe planets now is via transits. The way that works is if you have a system which is inclined as such that a planet can actually run across the surface of a star, or run around the surface of the star as it's orbiting, and you look at the brightness over time of that star, you can see these dips. And they're periodic. They'll happen every orbit. So every time this planet comes around the front of a star, you will see, boom, light goes down. And we can time these, and we can stare at stars over very long times, and we can see these periodic dips that happen repeatedly. These dips give us evidence that there must be some body that is orbiting around them with some period, and we can then, depending on how big the planet is, work out some of the properties of it. So this method is really good, it turns out, at finding planets that are close to their stars that happen to be very large. So things like hot Jupiters that I'll say a little bit more about shortly. There's this method called the radial velocity method, and this relies on the gravity of the planet being sufficiently big that it's actually tugging on its parent star as it orbits. So what you can see in this image here on the far left side is a model of a star and a blue planet that's orbiting around it. But because of these being what's called a binary pair, they orbit around their common center of mass. And that means if this planet is big enough, the center of mass is actually shifted a little bit away from the star. Okay, so you can see that they're both orbiting around this common center of mass. And the result is, if you stare at the star, the light that the star emits wobbles. So if you look at the bottom right here, where this panel and you see this light, you can see these black lines. Now these are emission lines from the star that we know from our own sun can only appear in certain places. Now when they wobble periodically like this, it means that there must be something that's tugging the star to and fro in such a way that you get this repeating pattern. And much in the same way that we use the dips in the brightness for the transiting planet, we can use the period by which this moves and the speed at which this moves to categorize how big and how close that planet is to the star. In fact, this method is extremely good at finding massive planets around that are close to their parent stars as well. Also very good, for example, at finding hot Jupiters. Turns out hot Jupiters are really easy to find. And then we have this method. I think this is probably the most convincing as far as I'm concerned, when you can see planets, physically see them, orbiting around parent stars. And this is called direct imaging. The direct imaging, you can see in the very center, you've got some dot and then some black ring. Don't worry about that. That's literally just observers putting a mask over the stars so that you can actually see the planets. But what you can see here are these 4 dots that are going around in this sort of circular orbital pattern. Okay, and all 4 of those things are planets. So this is a system HO 8799. We know that it's got 4 giant planets, and this system is young. What's important about that is the planets that formed pretty recently, they're still very hot. Because what this method is very good at is finding bright planets that are very far away from their stars. If any of those were inside that coronagraphic shading region, inside that black region, we wouldn't have a chance of seeing them because it's covered up by the brightness of the star. Whereas because these are quite far out and they're quite faint, and they're quite bright, sorry, it means we can actually see their orbits as they're orbiting around their parent star. Okay. Add 30 years to the mix, having those methods, and actually a few more that I've not talked about, because I want to talk about some other things. And you end up with a plot that looks like this. So every planet we have detected up until August 2020, it turns out, is on this plot here. And this shows the mass of every planet that we've detected up until that date, and the distance away from its parent star that it is. Okay, so when this is AU, that just means astronomical unit, and that means how many factors of the distance between the Sun and the Earth this is. So 10 to the 0 here, this just means 1. Earth would be along that line, and Earth is about this massive, so Earth would be somewhere like here. So you can see that we have this huge number of detections of planets around the stars. Then if I plot what our solar system looks like versus those things, and the different instruments that those are detected by, where you can see transits account for the things that are in red and orange, radial velocities are the things in yellow, microlensing in blue, dark blue, and light blue, I guess, up there as well, is direct imaging. Now, if I look at where the gas giants are, so this is Jupiter here, this circle, just underneath the word giants, it looks like actually we can detect Jupiter around the stars pretty well. But when it comes to things like Saturn, well, that gets a bit hard. We don't have many things in the universe that we've detected so far that look like Saturn. We've got nothing so far that looks like Neptune, nothing so far that looks like Uranus. Turns out nothing that really looks like the Earth. We've got some things that are close, but nothing that looks like the Earth yet. We've got nothing that looks like Venus. We've got nothing that looks like Mars. And Mercury's down here. Certainly we've not got anything that's sensitive enough to find that. So it begs the question, doesn't it? Is our solar system rare? Are these planets that are formed around our star exceptional? Because as far as this plot's concerned, pretty much all of them look like outliers. I'm going to argue not, and I'll argue not sure. I want to talk a bit about the statistics here. So when we look at other stars and we say, okay, well, how does our solar system compare? We can see everything up here, and these are the so-called hot Jupiters. These are the giant planets that happen to be in like the orbit of Mercury. Okay, the really easy things to detect, the transits and the radial velocity searches. Now, although they are really, really highly populated on this plot, actually, for every star that we look at, only 1 in 100 actually have one of those. We just happen to have looked at lots of them to try and find these planets. So only 1% of stars have these hot Jupiters. Okay, these outer giants also, actually, although there's quite a lot here, maybe these aren't too common either. But they're also very hard to find, as I said, because you can only look at young stars where planets have only recently formed to find them. Exojupiters, it turns out, due to things that look like our planet Jupiter, around other stars, form around 1 in every 20 stars. I think that statistic's quite good because we know from the sensitivity of the surveys that we've looked for planets with so far that Jupiters are forming at a fraction of around 5% of all stars. Now, I think Jupiter's pretty important. I'll say why later. And I think that's quite important statistics to bear in mind when it comes to whether or not the solar system is rare. Because certainly, if we need to find an exosolar system, it's going to have one of these. And that means only 1 in 20 of all the stars that we've looked at do. Finally, terrestrial planets. Now, although Earth, Venus, Mars here, terrestrial planets in our solar system, we don't have many things that look like them yet. It turns out terrestrial planets that are broadly in this region here are forming around 50% of stars. And that means that they are pretty common. Like 1 in every 2 stars is forming rocky bodies. Okay, that's common, and that's actually very encouraging when you think about the potential for life around other stars. And then in a very, very short statistic here, and that's actually if you then start looking at the ones that are like our sun, the sun-like stars, it's about 1 in 5 have these rocky planets as well. Okay. So is the solar system unusual? Well, in this plot, it looks like it. But the way I try to imagine this is imagine you went fishing in the sea and you took a net, and the net was only big enough it could catch a whale. And you pulled that net out of the sea and you said, okay, I've got a little whale. So I'm going to note up here. And maybe every now and then you get like a big shark or something. But would you conclude from that plot that the only thing in the ocean is whales and giant sharks? No. You would conclude that your net isn't quite good enough yet. You need a finer net. You need better searching techniques, and that's basically the problem at the moment. Our planet, basically the catalogue of exoplanets that we've observed so far, has been constrained by the detection sensitivity of our experiments, of the instruments we've had available to us. And that's not to say they've not revolutionised our understanding of the universe, because this is quite frankly remarkable. All of this has come around in the last 30 years. But it does mean we need to go deeper. We need better instruments to able to actually detect everything that's in these regions as well. Because it turns out, I would imagine, that these things aren't going to be that uncommon at all. Okay. when anyone asks me what I'm doing for my PhD, and I try to make them excited, I struggle because they say, okay, so what do you actually look for, Josh? And I'm like, well, I try and find dust around other stars. No one's excited about dust. People might be a little bit excited about gas. But what I try and explain is actually dust is incredibly important. And one of the reasons dust is so important is what dust traces. Okay, and dust traces things like collisions. It traces places where planets can form. So here's just an artist's impression here. And this is probably an asteroid type belt somewhere in the universe. But what's happened here is two of these asteroids have collided. And when they collide, they pump out tons of dust, so much so that it actually becomes observable. Okay, they also, it turns out, have gas locked inside them as well. So when these things collide and smash into each other, they chuck all of this dust and gas out. And that I think is exciting. So although like trying to explain that looking for dust is quite cool, I think it is, and this is why. The way that we look for dust, primarily via two ways. The two ways at least I'm going to talk about. I guess there are some others. But we look for dust because dust can scatter light, at least reflect light, I would say. Scatter light from the central star. So when the star shines and hits these rings that are formed around it, where these collisions have happened, these light, the light hits the dust, and then that shines back to us in our telescopes. Okay, and actually, the dust that is forming in these collisions, in these belts, survives for long enough, and the collisions are frequent enough that some of these actually become detectable. The other way we can look is by looking for the re-emission of thermal light. So every little speck of dust in this belt has some temperature, it therefore has some thermal emission component. And if you add up every single bit of dust in one of these rings, it actually becomes visible. And you'll have to trust me for now that that's the case. And I'll show you some images to demonstrate this is exactly true. So taking the first of those, the scattered light. So what I've got here is a picture of Hubble. The Hubble launched a little bit before I was born, I think about 30 years ago, a few more than 30 years ago now. And Hubble opened up the detections of planetesimal belts. So Beta Pictoris, as you can see here, Beta Pictoris is also covered up by one of these coronagraphs because its star is so bright. But if you cover it up, what you can actually see is the belt of dust that runs across the planet, across the star. Now, what you can have to imagine is you're looking at this thing side on. If you looked at it from above, that would actually be a ring. Okay, that's actually a belt of asteroids that have been colliding and colliding around this system, which is about 20 million years old. If you're interested, ask me why there's this primary and secondary disk in the questions. I don't have too much time to explain that now. Also, if you're really interested, it turns out you can do all of this from the ground. I only found that out today, and I found it quite remarkable. But it turns out someone 10 years ago actually imaged this disk from a ground-based telescope with amateur equipment. So it's probably possible that someone here, if you're really inclined, you could actually go and find this in the universe itself. The other way that we look for things is through thermal emission. And primarily over the last 10 to 20 years, our detections have come from two instruments called Spitzer, which is this thing here, and Herschel, which is this thing here. And unfortunately, both of these things have been retired. One of the problems with space telescopes is they only last so long. It's actually hard to get to some of them, to fix them if they've run out of fuel. But what these have been able to do is look at the longer wavelength emission. So here, this is Herschel, this is like 100 microns. So we're looking at dust that's a bit bigger than the scattered light stuff that we saw with Hubble. And what you can actually see here is the ring of emission around the system Fomalhaut, which is a bit older. It's about 400 million years old, this star, and this system. And what you can see is the star itself and the belt of dust that's forming because of debris, because of this dust that's formed in collisions. Okay? So these instruments have really revolutionized our understanding of how commonly these types of belts, these exo-Kuiper belts, Kuiper belts and asteroid belts around other stars actually are. Okay? I couldn't carry on this talk without talking about ALMA, because I use ALMA. ALMA has allowed us to peer at even greater detail at what these belts actually look like around young stars that have got protoplanetary disks that I'll talk about shortly, and around older stars that have these debris disks, these collisional disks. Okay, the way that ALMA works is it's an interferometer. It therefore has 66 dishes, although I don't think all of them are there at the moment, in this image certainly. It's got 66 dishes, and what it effectively does is create a telescope which is as big as the area on the ground that it would cover. So you can imagine this red ring as being one giant telescope that's had loads of holes punched out of it. And that's kind of how this interferometer works. So the bigger the telescope you have, the finer the resolution that it can actually see with. So what this means is this has the resolution of a telescope. It could be 150 meters or even 16 kilometers. Okay, and that's actually like enormous, right? Not quite as big as the one that we used recently to detect a black hole. That used the entire Earth by basically using telescopes on the North Pole and the South Pole and combining all of their baselines. But anyway, 16 kilometers for a single instrument, I still think is quite impressive. Okay, formal what I showed you was that blue ring, whereas formal with Herschel is the blue ring. Formal Holt with ALMA, however, shows this this system here. Which, if I show it as a comparison, when you think about the sensitivity with which we can actually detect what's going on inside these belts, ALMA gives us a much sharper view of what's going on. So this looks much more spread out, and the reason is it's sort of grainy. This is basically, look, imagine you're just squinting at this thing. It's sort of like giving the image a bit of a haziness. Whereas what ALMA can do is really show you the structure of these belts in much finer detail. The sensitivity and the resolution is just much sharper. So it's been able to let us look at longer wavelength emission and at higher resolution. It's done wonders, in fact. So all of the various things that I showed you in that image at the start, hopefully now I've given you an idea of how you can detect it. Okay, you know, gas and dust that forms in comet collisions and asteroid collisions, we're going to use ALMA to find. Radio velocity tugs, we're going to use radio velocity surveys to find, etc. Okay, the takeaway points at this point are that the planetary system components include all of these things. They're all important, and we can detect things that are going on either directly, so we can actually see planets, for example, with imaging or with radio velocities, or we can actually look for things indirectly. We can't actually see asteroids around the stars. What we can see, though, is the dust that was created by them. Okay. I want to talk now about planetary system formation. And I'm going to give a very brief model as to how planets, well, firstly how stars form, but how planets can form around them. And I should start here, okay, back to this image that we started with. And that is that we've got this giant dust and gas cloud, and that's about 1,000 light years across, so it's quite enormous. And what you can see in there's these filamentary structures. So an example is one's there. And you get overdensities. In fact, you can see, I think, just there under my red cursor is the Horsehead Nebula. And these overdensities are places where there is sufficient amounts of dust and gas present that they're gradually collapsing in on themselves under gravity. Okay, and give it 100,000 years or so, and eventually there's enough matter that you get the formation in the center of these overdensities of a protostar, a star that's still forming. Okay, somewhere where there's lots of matter falling onto the surface of the star, so it's growing in mass, but it doesn't quite use up all of its material. Okay, and we've seen some of these things, so we can actually image these. So here are some HST images, Hubble images of 3 young stars that have only recently formed, and you're going to have to imagine this turned on its side with lots of dust along its midplane, so you can't actually see where the star is. And this yo-yo is actually a protoplanetary disk that's forming around a very young star. And these things form jets because as matter falls onto the star, it's basically producing lots of hot ionized gas. And that ionized gas is being rocketed out into the interstellar medium, and it's hitting material and causing shock waves, basically. And we get these beautiful structures that can be seen with Hubble. So this is Herbig Howard 47. You can see it's just these enormous jets being blown out. And that's a star forming inside there. But I think the star is about there. I would need a higher. I probably need to not be looking at this screen with these dots on it to see it. A little bit of time passes, and the material that's falling into that star is falling in mass because the star is taking it off. And what we end up with is a system where you've got a little bit of infalling mass, and you've got some small jets, but broadly speaking, we've got this very thick protoplanetary disk. We've got somewhere the matter can start to accumulate in the same way that it did to form the star, but into protoplanetary material, so into planetesimals, things like asteroids, things like planet embryos, okay? Places where dust coagulation, basically the particles that were present in all of this medium here, are now gradually in such high concentrations inside this disk that they go on to form pebbles. Those pebbles combine to form much larger structures by themselves collapsing gravitationally through these instabilities. So the streaming instability is one mechanism you can use to create these much bigger things. Now these planet embryos can be kilometer sized, and those two can go forward and merge with each other to form much larger protoplanet embryos. Okay. Eventually, all of that material is eaten up, and you end up with very faint disks. Okay, places where there might only be a little bit of dust and gas left, but probably no giant planets can form, because giant planets require lots of material. Okay, and in this state is where basically collisions between planets are the primary mechanism which dust and gas is created. So I'm hoping this will play. Am I connected to the internet? Great, okay. There's no sound, so I'll talk over the top of it. But the basic broad model that I'm trying to describe is this. Once you have a planet, a protoplanet, or just a star, sorry, a protostar, and you have excess dust and gas in this disk around it, planet formation is going to happen, okay? And the way that it proceeds is broadly like this. You get these planet embryos that form in the way that I just said about these like dust coagulation and instabilities. And they form and they orbit around their star, and as they orbit around their star, they basically hoover up all of the dust and gas that's nearby them. They hoover up most of the dust to form these solid bodies, and then for giant planets, they hoover up all of this gas around them. So you can see that eventually the protoplanets go on to form giant planets themselves. Okay, and this is probably how planet formation might look if you were able to go to a protoplanetary disk and sit there for 10 million years. This is probably what you'd end up seeing. Unfortunately, we don't quite have that much time. So what we have to do is look at stars at different ages to understand that that's what's happening. There. How do we know this happens? We know this happens because we've seen it, okay? So this image was taken in the first year that ALMA came online. That was only 10 years ago. But this image came out about 3 or 4 years later after we'd worked out how ALMA worked. And this is HL tau. And this system is like 100,000 years old or 1 million years old, depending on who you ask. What you're actually seeing here are these rings that are formed because planets inside here and inside here and inside here probably have carved out the dust. They've formed protoplanets that are inside these rings, and they're actually now forming giant planets as we speak. So this is all dust, and this just took 7.5 hours of ALMA's time. It is really, really revolutionary in terms of what we can understand about the universe. For scale, everything inside that dotted line would be in the solar system, at least out to the Kuiper belt. So as far as the Neptune plus 10, 20 AU. Okay, so all of the asteroids and comets in the Kuiper belt broadly fit inside that. So this thing is actually pretty big as well, and it's not unusual either. And I'll show you a few more shortly. I think I've just shown here. I don't think the screen. Maybe hopefully at home this is a bit more visible. I'm not sure how visible that is back there. But broadly speaking, what you can see here, these dashed lines here, these rings, these are literally formed from planets. Okay, and this is how we know that this is a common thing that occurs. HL tau isn't an oddball. This is an image from the D-Sharp survey of protoplanetary disks, and it turns out substructures in protoplanetary disks are extremely common. In fact, pretty much all the ones that we're looking at now that are large, we're finding that they have these ring structures. Some of them have clumps in them. Some of them have spirals. In fact, if you were looking at that, you might be forgiven for thinking it was a galaxy, right? It's truly quite extraordinary. That one in the top middle, if you're listening at home. You have all of these substructures that form, and the reason these substructures form is because giant planets are embedded inside their disks. Okay? So these giant planets are common inside protoplanetary disks. And protoplanetary disks actually have a lot of mass in them. If you look at each of those purple disk areas, you can count up all of the flux inside them, and you can basically weigh them. And if you weigh them, some of them weigh about 100 Earth masses to 1,000 Earth masses in dust. Some weigh even more in gas. They tend to be gas-rich. And what that means is if Jupiter weighs about 320 Earth, some of these things can form 10 Jupiters planets. Some can't actually form any. Some are so low mass that actually the formation of giant planets might even be inhibited. That means that young planetary systems form planets with a range of masses. And it's basically set at this stage here. It's set by how much material has fallen onto the star, or been blown out of the system, of course. So protoplanetary disks are gas-rich, and I'll explain shortly why that'll become quite important. What I wanted to do briefly, though, is discuss in short a result that came out this summer. So Alma, again, I'm going to say Alma a lot in this talk. Alma again looked at a protoplanetary disk around a star called PDS-70. The star is at the very center of this image. You can see some dust around it. And we know about this protoplanetary disk for some time, by the way. We know that it's got protoplanets in there. You can actually see one of the protoplanets. But it turns out if you look with high enough resolution and you zoom in, there's more than just a protoplanet there. Not only have you got a protoplanet forming with about 4 times the mass of Jupiter in the center, in the middle of that ring you can see this excess dust. Okay? And this was announced this summer as actual proto-lunar material. There's moons forming in the system perhaps as well. Or there's been a recent collision with that protoplanet. Okay? So there's all this excess dust that might actually go on to form an exomoon. Okay? And this hasn't been seen before. So this is really exceptionally exciting, because if we can understand how moons are forming around other planets, then we've come a long way, right? So far, I've sort of just explained giant planet formation. I think it's important to talk about what's happening in the inner solar system as well, in the inner regions of planetary systems that are much closer to the star. Because giant planets, you know, sure, that means that we know probably how Jupiter's form and how Saturn's form. But we should talk about how terrestrial planets form. Okay. So we'll do a show of hands on this one. Given that the temperature is decreasing as you move away from the star, I mean, maybe it's obvious from the image, but where do you think planet formation is going to be faster? Hands up for closer into the system. Hands up for further out. Okay, interesting. So what I'm going to talk about is the ice line. Okay, the ice line I've just set is somewhere in here. So a region that broadly separates where terrestrial planets are going to form, which are predominantly rocky bodies, and where giant planets are going to form, which are predominantly gassy bodies. Okay, and the ice line within which everything is ice poor, and the reason is that water and ice inside this region can't actually exist in a solid form. It's too hot. So it's all formed, basically the only ice and water you're going to find within this region, broadly speaking, is in a gaseous form. So it doesn't stick together. Out here, however, where you're in an ice-rich region, things have a higher water content. Okay. Now imagine trying to stick 2 rocks together. Now, unless they've got lots and lots of gravity, they're not going to stick together unless they're really big, right? If you make things a little bit icier, things stick together much better. Okay, and this is one mechanism at least, and it's a model to explain why we think planets might grow quicker in these outer regions. And that's because if they've got more bodies there that are sticking together faster, that in the protoplanetary disk they can form larger structures much faster, and therefore conglomerate more gas quickly. Okay. So I've said earlier that protoplanetary disk gas is important, and I'm going to explain why. So this is the terrestrial region of a young solar system that I've just defined here. There's something that's got loads of gas around it and some planets. Now, because the star is radiating now, it's not a protostar anymore. It's basically blowing away gas by radiating it, and some of this gas is actually being eaten up by the planets either here or some of the planets out here. So over time, the gas is basically falling. And what that gas does, it acts as a damping force on the planets that are present. It means that when they orbit around their star, the little kicks from gravity that they would give to each other are sort of damped out by the gas that's present. As the gas disappears, the damping is less. And as the damping decreases, it eventually means that once the gas is gone, these things can actually cross their orbits. They start to intersect. Now, what can you imagine is going to happen in this system now? Well, these things are going to collide quite violently. And that's indeed what we find happens around other stars. And actually, it's one model to explain how our solar system formed the terrestrial planets that it did. Because it probably started, and this is, I have one model, there are other models. it probably started with a wide range of planetesimals and planet embryos in the inner region that weren't very massive because they weren't able to conglomerate much larger planetesimals in time, not certainly before Jupiter was able to. And as these things collide, they gradually grow. So it's the collisions between these planet embryos that's actually creating ever such larger bodies. Okay, and that's indeed what this diagram is basically showing. Over 500,000 years, 1 million years, 10 million years, 40 million years in the final plot, you end up with structures that look a little bit like some of the solar system planets. Okay. Why is that important? Well, that's important to explain where terrestrial planets might come from. Okay. And in fact, it's also where we think some of the terrestrial moons that we know came from. In fact, it's where we think that mechanism basically is how we think our own moon came to be. So what we had in the early solar system was lots of these early planetary bodies. And what we had is here what are called proto-Earth, and this body Theia. And Theia and Earth were quite near to each other in the young solar system. I mean, apparently this happened about 100 million years after the formation of the Sun. But there was a giant collision between this proto-planet here, Theia, and this proto-Earth. And it probably looked a little bit like this. This is just a diagram to explain how we think these collisions occur. So what you can see is this planet here, Theia, is gradually falling towards the young Earth. When it collides, it smashes into the Earth and produces lots of dust and gas and planetesimals that then go on to orbit the Earth. Okay? As that cools down and conglomerates, that forms the moon. And that is one of the best explanations we've got for why the moon, or how the moon forms. Okay? So there are two things that we can understand might have happened during that process. Okay? If that thing smashes into the Earth, it's going to pick up some of the Earth. Okay? It's actually going to have potentially some of the material that's on the Earth present on the moon today. If that impact happened at a particularly high speed and actually formed a magma ocean world that orbited the Earth for some time, then probably some of the processes on the moon that formed some of its material aren't geological after all. So they might actually, in fact, just be as a result of like material being warmed up to a magma sort of state and then cooled down. And these two things are testable. And indeed, we have tested them, and it turns out this checks out. So if you look at the oxygen isotopes on the rocks that we look at from going to the moon and actually picking them up and bringing them back down to the Earth, and comparing them with samples of rock on the Earth, then actually the oxygen isotopes look the same. So one of those tests works out. And in fact, if you look at the zinc content on the moon, these things look depleted. More depleted certainly they would if certain types of rocks formed through geological processes. So actually these two things actually appear to be the case on the moon. So the best explanation of the existence of the moon is there was this giant planet impact early in the solar system. We also think this is happening right now around other stars. So this result came out on arXiv yesterday, but about 10 days ago in the press. And that is the detection of gas around this star, HD 172555. In fact, some of the people on this on the author list are here in Cambridge. And what we think is happening around this system is there's been one of these violent collisions very early on. This system is much younger, much younger than our solar system. This system is something like 12 million years old. Okay, but what we think has actually happened here is gas has been produced in the violent smashing of a young planetesimal or a young protoplanet into another. Potentially there's going to be some moons forming here as well, but that's going to take a while to form. So I think the takeaway points here on planet formation is that this is a natural byproduct. When stars form, planets will form. Okay? That the formation proceeds differently depending on where you are in the protoplanetary disk. So we get terrestrial planets that tend to form towards the inner region of the system. We have giant planets forming towards the outside of the systems. And that's ignore that third one. I had to cut this talk down because it wouldn't fit in time. I apologise. How do planetary systems evolve? So I've taken you through formation. Now I'm going to talk about evolution. So what I showed you earlier was the protoplanetary disks in the D-sharp sample. But we found out in 2018, these were something like 100,000 years to 10 million years old. Okay, if we look at much older systems, some not too much older, but if we look at main sequence stars, we see these things called debris disks. Okay, and all of these are at least twice as old as any one of these, and some are hundreds of times older. So I know, for example, Q&A, I spent a lot of time looking at that system in particular. That's probably 1.5 billion years old. And yet it's still got one of these disks. Okay, it looks actually pretty much similar to one of these, right? But what's happened in these systems is very different. The evolution of the substructure here is very different to the evolution of the substructure here. Okay, and the reason is what's happening in these systems, these young protoplanetary disks, is they're forming planets. Okay, whereas what's happening in debris disks is that planets have already formed, and what we've got now is the reprocessing of all the dust. So the dust that went on to form planets and planetesimals is now colliding and basically being recycled. Okay, so the structures here are a result of collisions between asteroids and comets. The structures here are a result of planets actually hoovering up the dust and gas. The gaps in the system, on the other hand, are probably as a result of the fact that planets have formed and no planetesimals can actually survive within those regions anymore. Because, as you can imagine, if you think about the solar system, between Jupiter and Neptune, there's basically not many asteroids at all, right? Then you get these two belts between, so the asteroid belt and the Kuiper belt. And the reason that we've got these big gaps, therefore, around other stars is because planets have probably formed in these regions, and now collisions are not able to happen anywhere near as frequently as they do in regions where there are planets. Okay, so I guess what I want to say to underline here is these are all sort of exo-Kuiper, the Kuiper belt in the solar system. That's exactly what we're looking at here. And the reason they have substructure is because planets have already formed, probably. We don't know that for sure because actually it's very hard to see. All the planets that would be in these regions are so cold now because they're so old. It's actually very hard to detect. I want to talk a bit about a couple of systems in particular, about why we think they're the shape that they are. So here's one for Hubble. So Hubble 2004 looked at Hubble, and it found this beautiful ring of dust. This is all dust that's forming again through collisions. And if you look at the inner edge on the right-hand side of this, and if you looked here in 2004, and then here in 2006, and here in 2010, and here in 2012, in this central blow-up, you saw this bright point of light. And this bright point of light was following the inner arc, the inner edge of this disk. And people said, well, okay, well, that must be a planet. Because it looks like you're directly imaging this thing, right? Much like the system we saw at HRI 799, where we had the blue image of sort of planets, it looked like we had a sort of stop motion version of that. Okay? And maybe, therefore, this system is being carved by that inner planet. Turns out that might not be the case. And this is something that came out earlier this year, I think, or maybe late last year. And that is, if you look at the brightness of that point over time, it's orbiting around the inner edge of Homohobb's ring, it's actually getting fainter. Okay? If it was a planet, why would it be doing that? You would need a peculiar explanation for that, wouldn't you? Because you would expect a planet that needs to be a constant brightness that's going around its orbit. Instead, this is getting dimmer and it's getting bigger. Or no planets I know of do that. Okay? So this now instead looks like it's actually that bright spot is probably a collision of an asteroid in the inner edge of the belt that is now actually fragmenting and expanding as it's moving around the orbit. Imagine, if you will, imagine a giant snowball. If you threw a giant snowball together, immediately it would be all the material would be very close together, and over time the material expands. And over tens of years, you can see here, just 10 years from here to here, we've gone from something which was small and bright to something which is now much more broadly expanded. So it's possible that that system isn't in fact carved by a planet. Okay, some of the others might be. Another one that I want to look at is a system Q&A. I guess the reason is because I'm quite familiar with this one. So Q&A is another one of these disks, and what you'll have to imagine is this is very much like Hubble, but the disk is much wider. Okay, so the disk here in Hubble is very narrow. probably only 10 astronomical units wide. This system is like 140 wide. It's actually enormous. The disk is very narrow. Whereas this system is probably only 80 AU, so 80 times the Earth-Sun distance to its peak, but its width is probably about the same. So it's extremely broad. What that must mean is that planetesimals and asteroids formed over a much wider range of radial distances from the star than they did in Formable. Otherwise, this would be a much narrower belt. Okay. So what we've got therefore is this gap in the center, this gap where there's probably planets. In fact, I know in this system there is definitely a planet that's about here, because we've looked at this star with radial velocity imaging and we know there's an exo-Jupiter in there. That's one of the reasons we looked at it. However, you've got this great big gap then where you don't get any emission, and then all of a sudden you start getting collisions again. If you also look at this side of the disk and then this side, you find that the right-hand side is brighter. There's just more material. There's more material there, it means there's more dust there. It probably means that collisions are happening faster in this side than this side. Okay, this isn't an eccentric disk either. If you looked at this from above, it would be a circle. It would be a disk. Okay. So what makes this point special? The way that we analysed it was to say, well, we've got a gap in the centre, and that gap must have been opened up by planets, perhaps. Why is it that we've got this broad 30 AU to 40 AU gap? Well, perhaps some planets formed over a broad range and moved outwards. And what's happened, perhaps, is that as a planet swept outwards, very much like we know Neptune did in our solar system, it can actually trap planetesimals in what are called resonant orbits. Okay? So its own gravity is enough to actually get other planetesimals entangled in its own gravity. And that means if you get a larger density of asteroids and comets in a particular region around a planet, these collisions happen more frequently, and you end up with much higher levels of dust on one side of the disk, or at least where a planet has migrated out. Now, I add that's possibly not what's actually happened here. There are a number of reasons. But we think possibly the most likely one is that an exo-Neptune formed here, migrated outwards like it did in our own solar system, and actually has created lots more collisions in this region, and therefore a higher flux on this side of the star. So the takeaway points then, at this point, I would say, these planetary systems are evolving over billions of years. That's 1.5 billion years old. That's at least 400 million years old. So these systems can live for a very long time. For instance, planetary disks have gone after 10 million years, right? These things are here for a very, very long time. We can observe them because asteroids and comets are colliding, and the structures that we actually see are dominated by when and where collisions happen in these belts, and by potential perturbations due to planets that are in these systems as well. So I think at that point, I've probably got a little bit of time to talk about the next generation of observatories, and then I'll probably finish, because I don't think it would be talk about observational astrophysics without going into what was coming next. Because I guess from some of the things I've said, it sounds like we've got good answers for a lot of things, but that's not actually the case. There's still loads that we don't know. Still so many questions unanswered. I put some of them here. We don't actually know how common Earth-like planets are, not ones that are in habitable zones around sun-like stars. We think we've got an idea of how common some of the terrestrial ones are, but certainly not exo-Earth. Not seen an exo-Earth yet, so we can't really tell that. We don't know how many of those actually have atmospheres, how many of those could actually have life-bearing chemistry, actually how many of those could have biology. We don't know how much the planetary atmosphere is a result of the formation of the planet, when it was probably hoovering up lots of hydrogen and helium, and how much of that is because of delivery from asteroid collisions that happen. So, for example, the water on Earth is probably there because of asteroid belt collisions. Actually, the region where the Earth formed is probably too dry and too ice poor to actually explain where all the water on the Earth came from. How common did that happen in the systems? We don't know. How common, how necessary is it for a Jupiter to form to actually protect the inner regions of the solar system to ensure that life evolves? We don't know. There are all of these questions, and we have a number of instruments I think are going to point the way to towards giving us some answers. And I think one of them, and as I said, it's obligatory, I think, at this point to talk about James Webb, because it's going up next month. It's next month now. And I'm really hopeful it's going next month. One, because I want to get some data from it. And two, because it's going to answer some of these things I've just said. So James Webb is this near and mid-infrared instrument. So it's looking at similar wavelengths to what I said Spitzer did earlier. So it's able to actually detect dust belts and protoplanetary disks. And it's also able to look at the inner regions of planetary systems. It will be able to see planetary atmospheres around certain types of planets. It will be able to find dust and gas and comets that might be giving material to young protoplanets and formed planets, in fact. So this instrument is doing a lot, but for planetary astrophysics, it's going to be extremely useful. The reason I say it's going to be doing a lot because it's also looking at the evolution and formation of galaxies. It's trying to look at the cosmic origins more broadly, but it's also trying to understand how stars and planets are formed as well. Other things that are going up soon, Plato. So Plato is this mission by ESA, and that's probably going to be launched maybe about in 5 years or so. We'll see though, because engineering projects are likely to run over. And the idea of Plato is to fill in this region here. But I think it's only empty though, as I said earlier, because our sensitivity is not good enough. Plato actually won't be able to look into this region. And what makes Plato so interesting for me, certainly, is that it's actually going to look at the sun-like stars in particular. So a lot of these surveys didn't care what type of star was there. So a lot of them are around like very, very, very faint stars. It just so happened that you can find transits. What this telescope is going to look at is stars very much like the sun, and try and understand how many terrestrial planets are forming around sun-like stars. What's cool about Plato as well is that it's going to look for transits, and then it's going to look for radial velocity surges. So the transit, you can get the size of the planet. The radial velocity, you can get its mass. And if you know the size of something, and you know the mass of something, and it's a rocky body, you can make some assumptions about how dense it is. And what you can start to do is say, well, where would it fit on parts that look a bit like this? You know, is it got a density that looks similar to Earth? Has it got a density that's similar to Jupiter, to Venus? Rather? Okay, so Plato was to try and fill in regions of parameter space that look like this, and actually try and detect exovenuses and exo-Earths. Other things, there's lots. This week on Thursday, NASA will announce their decadal review. Okay, and what this means is every 10 years they'll like to go, what the big questions that are coming up. And the OST, that's the Origin Space Telescope, that's like a Herschel replacement. And what I said earlier about how good Herschel was at detecting young disks, that is one of the options that could be selected. HABEX, Lovell, these are planetary detection missions. These will potentially find habitable exoplanets. We're not very thoughtful with our names sometimes. This Lovell literally means large ultraviolet optical infrared telescope. These things could be selected and they could be going into the sky in 10 years' time. Later this decade, we have the European Extremely Large Telescope. Again, another unimaginative name. And that's a 40-meter class telescope. That's simply enormous. It's so big, in fact, that it's going to have a sharper imaging than Hubble, even from the ground, by over an order of magnitude. It's going to be quite extraordinary, in fact. Okay, and there are more. I'm not going to list off all their names, but there are other things that are being considered. There are some things that have been selected that will be going up soon. There are some missions like TESS right now who are every day or two, I get an archive update, so there's a new test planet found. Okay? So these things are constantly being updated, renewed, and improved. So we've got a lot to look forward to in the next 5-10 years. There's still lots left unanswered, but we are actually entering an era when habitable zone rocky planets are going to be detectable, and potentially, depending on which is selected by the NASA decadal review, but definitely because James Webb is going up, a period that we can actually start to look at the formation processes in the interterrestrial regions where we could see asteroid belts and planetary atmospheres around young planets. And just to sort of say how far we've come in the last 20 or 30 years, you know, it was 1984 that the first debris disk was detected. It was 11 years later when we found the first planet around a main sequence star. Okay, 51 pegs. And then like 20, 30 years later, We're on 4,500 confirmed planets. We've got another 8,000 candidates that are yet to be confirmed. We've got hundreds of debris, we've got thousands of protoplanetary lists. And just to give you some idea of how quickly that's come on in the last few years, is that it was only, what, 6-7 years ago that we were at thousands. This has been expanded on so much more recently. Okay, so if you are an aspiring astronomer, this is my pitch to say now is the time to get involved in planetary science, because there's so much data now, and there's so much new stuff coming online soon that who knows how large this is going to go by the end of the decade. Okay, so I'm going to end here because I've probably gone on for my hour, and that is, I just want to say at this point that we've really come a long way. We've got an idea of how our solar system formed and evolved. We're now looking at how exosolar systems formed and evolved, and we're using those to understand the processes that have gone on inside our own. Okay, and the things that we see and we expect to have happened in our own solar system, giant planet collisions, giant planet formation, we can now see happening around other stars. Now, it might be that our solar system is exceptionally rare, but it might not be. Certainly, we know that the processes that formed our solar system are ultimately very common, because we're seeing them everywhere now. And that's only been possible in the last few years. So I'm going to end there. Thank you.
Thank you, Josh, for the very interesting talk. Now we have about 15 minutes for questions. If anyone would like to ask a question, please raise your hand and I'll point to you. We can also try to take a few questions from the online audience. So if anyone watching over Zoom has a question, you can put it in the chat. Any questions from the live audience here? Right, the lady over there.
So, you know how hours all the time is that something like that?
It might be. I don't think the inclination distribution of planets is well known. But you'll recall what I said earlier about, I'm going to have to jump back a lot of slides. I'm going to try and do this in a way that means I don't lose track entirely. Because what I want to show you is that picture of the beta pic image from Hubble, which is much further back. And the reason I want to show that, trying to speak so it appears by the time I've got back to it, this is when you maybe got to these slides, is that, as I've said, the image of beta pic, you can see that there is this secondary plane of dust, right? So if we look at, oh dear. Text been exceptionally good from my part. Right, okay, here we are, in current slide. Okay, so they do have some misalignment, by the way, but it's not particularly big. But what you can see here when you look at beta pic, there is actually a secondary band of dusting. Okay, so you get this primary disk and you get this secondary disk. And the reason we think there's a secondary disk around beta pic is because one of the giant planets in the system isn't aligned with the plane of the rest of the planets. Okay, and what that's doing is perturbing planetesimals onto inclined orbits that are then colliding at an angle to the rest of the plane of the system. So what you can see here is this bright band from the primary set of debris. And what you've got here is, because a planet on the inside of those is orbiting, I guess, at like that sort of angle, it's actually scattering them onto higher orbits. And therefore, we've got evidence that there must be inclined planets around other systems. Certainly, we've seen inclinations in other planetary systems as well, based on transits and where planets are crossing across their stars. But I'm not aware that we've got a good understanding of how the distribution of inclinations differs. But certainly, things aren't all in the plane. Okay.
All right, for the next question, Josh, if you could just repeat the question for the audience to hear online.
Sure, yeah.
So anyone else would like to ask a question? Right.
So how common do we think that non-axis and axis features like the one you showed in Q1 area, and how does that compare to the celebration on this stage?
Interesting. So one of the annoyances of debris disks is they're really, really faint. Okay, and that means you have to look at them a lot longer, and you have to look at protoplanetary disks to see the same level of substructure. If we look at, I wish I'd shown a picture of HL Tau before Alma, because this would have answered the question perfectly. If you looked at the picture of HL Tau, that's the big red protoplanetary disk. Sorry, I should have answered it. I should have repeated the question, shouldn't I? The question, sorry, was how common are the substructures around the debris disks that we see, so the old disks that I showed. So if I looked at a picture of HL Tau, that big bright red protoplanetary disk, this thing, before ALMA, you wouldn't have seen anything like this at all. You'd have seen like a very bright bit in the middle, and you'd have seen like a big, broad, sort of like dusty structure. It had probably looked a little bit like quaternary disks. Okay. However, when you look at extremely high resolution, the substructure becomes apparent, becomes quite visible. Okay. These things are maybe 100 times brighter than debris disks. So for an hour looking at this thing, you get all of this structure. I mean, this is 7.5 hours. But I know that if you look at a debris disk for 7.5 hours, you get something that looks a bit more like quaternary that I showed you earlier. So you don't get anywhere near as much substructure visible. But it doesn't mean it's not there. Okay. And in fact, one of my colleagues has been looking at the structure, the radial structure of debris disks more recently. And what he's been finding is that actually when you look at how much material there is to move outwards, you can start to see small perturbations on either side of disks. Okay? And even at the resolution that we're looking at with some debris disks, we're finding there is substructure present. Certainly there's substructure here because of this clump. Certainly there's some level of substructure on the inside of this protoplanetary disk. And actually, if we look at all of these things, HD 107146 has a ring-like substructure. HD 19945 actually has one bright belt there and then a broader belt out there. AU MIC, you can't see it in the millimeter wavelength images, but actually there is a weird feature that's basically being popped outwards when you look at it at scattered light images. So there's substructure in all of those. I've shown you substructure in one area. My view is that until we can actually get to the resolution where we're looking and resolving across the belts themselves, we're not actually going to be able to answer that fully. But certainly what I'm looking at here are images that look a lot like protoplanetary disks before ALMA. Okay?
All right, do we have another question? All right, we'll get the question. Sorry.
In our solar system, do we have enough frequency of collisions that a hypothetical observer could see any of our debris there?
Good question. The answer is no. So something happened some time ago that meant that lots of the asteroids that were formed in our Kuiper belts either scattered outwards, scattered inwards, and have already collided. And it means the mass of our Kuiper belt now is like a factor of 100 smaller than any of the debris disks we've observed. So if you were sat in Alpha Centauri, for example, looking back at our solar system, you wouldn't see it. So that also gives me encouragement that these like Kuiper belts, these asteroid belts, are really frequent. But again, we're just not able to see them because they're too faint around some stars. All of the ones that we're seeing here, these are the exceptional cases. So when we look around main sequence stars, we've seen these around about 15 to 20% of stars. But that's only because 15 to 20% of them are probably bright enough to actually be detected. Our Kuiper belt, you would just see nothingness if you looked at it from any other star system because it wouldn't be bright enough to see. So if you have a sensitive enough instrument, yes, you would see it. But certainly with what we've got at the moment, it would be invisible.